Okay, we're going to look at an application of extrema, maximums and minimums, and it's called optimization. Optimization means you want to take a quantity and either maximize it or minimize it. So that really is meaning we're going to be doing our first derivative test and finding out where there's a max or where there's a min. So we read this problem. The first thing you want to note is what dimensions will produce a box with maximum volume. So that's the key, maximum volume. We're trying to find the biggest volume. So that's the equation we're going to use here. We're going to write the volume of this box. We're going to call that our primary equation because that's the equation that we're trying to maximize or minimize. So we've got this box and it doesn't have a top on it. It's an open box. And it also says that its base is a square. So I know that those two dimensions on the bottom are the same to make it a square, and I'll call the height h. So if I write the volume for that box, it's x times h. So that's x squared h. Now, before I can take the derivative of this primary equation and find what x or what h produces the maximum volume, I need to get it into one independent equation variable. So we need one independent variable. So right now there's two. The way that we can solve that problem is when we set up a secondary equation that has the x and the h in it. So another reason for the secondary equation would be, look, if you think about this box, we want to say, what are the dimensions that would give it a maximum volume? Well, clearly, I could just make the x's as large as I want, the h's as large. I'll make them so big that I can fit the Earth in it. That would be a pretty big box, but yet I could still make it bigger. So the other purpose of this, or the other function the secondary equation serves, is a lot of times it provides you a constraint. So I can only make the box so big. So while we're talking about volume, the constraint is the surface area. The surface area has to be 108 square inches. So I know 108 can only be the area of the surfaces. So it can't be bigger than that. It can't be less than that. So the area of the bottom face is x times x. There is no top face. The area of the face of one of the sides is x times h, and there's 4 of those sides. So here's your secondary equation. Let's take a look here at what we're talking about. So these are all different boxes that if you notice their dimensions, if you were to do the surface area using all of these dimensions, like 4 by 4 by 5.75, if you worked out the area of that, it would come out to be 108. The same would be true here of my 5, and my 4 3/20, right? That would work out to be an area of 108, but yet they have different volumes, right? So these are just some situations of all the different boxes you can build. There's an infinite amount because you can make the sides all different sizes. So it looks like out of all of these, this one's our winner with a volume of 108. But let's do the calculus and see if that's actually the box under these constraints that have the biggest volume. And remember, those constraints are that the base is square, there is no top, and the surface area is 108 square inches. So I'm going to solve the secondary equation for h. So I'm going to subtract x squared off both sides. Whoops, forgot the subtraction. And then I'm going to divide both sides by 4x. So now I can use that equation back over here in my primary equation. I can substitute in for h what it's equal to. And this gives me all x's, which is nice because now I can do my first derivative test on this function. Before I take v prime, I want to simplify it so it's a little bit easier. I don't have to use product rule. I can distribute the x squared here because this power is 1. So I'm going to get 108 x squared minus x to the 4th all over 4x. I can then divide this x out with 1x in both of these. So my equation here is 108 x minus x cubed all over 4. If I want to run the first derivative test, I'm going to take the first derivative, and this will find me the x's for which my maximum, my volume becomes a maximum. So the derivative is 108 minus 3x squared over 4. So if I set that top equal to 0 to find my critical values, I get 108 equals 3x squared. Divide by 3x squared equals 36. Square root, I get negative 6 and positive 6. So now those are my critical values. I'm going to make a test interval for v prime. I don't need to test this area. I don't need to show that this is a max or min. I can't have a side with negative 6. I could have a side with 6, so I've got to test either side of that. So if I plug in 0 into that derivative, I get a positive. And if I plug in 8 into that derivative, I get a negative. So this is correct. We have a maximum at x equals 6. That's the length for x that would provide a maximum volume. So did I answer the question? They want the dimensions. So if x is 6, the other dimension is 6, how do I find h? Well, you can go back to your secondary equation over here. 108 minus 6 squared over 4 times 6. Let's see what that works out to be. That works out to be 3. So h is 3. So the dimensions are 6 by 6 by 3. And that happened to be the box that we saw on the other page. So that was the winner, even out of all the boxes that we don't see here. Here are some guidelines of what you can do, or how you can proceed in solving some of these problems. You can pause it here. I'm going to stop the video.